this is looking promising, I hope. There we go. I'll see if I can share a screen here. Okay, yes, I think it worked. Okay, there we go. Okay. So today, I want to talk about least squares, and I want to field any questions that might be coming up regarding homework. And I'm going to do them in that order because some people are already done with the homework, and I don't want to make everybody wait. Okay. Cool. So can you guys can see my webcam here, I think. And that's in focus more or less. So we started a conversation about least squares, regression. Last time, and least squares regression. Oh, hey, Cassie.
Hello.
Least squares regression, it takes data, be x1, x2, x3, and there's sub I here. So there's, so each of these columns has data, right? And then you also can have like function, a function of x1, a function of x2, a function of x3, right? And there's really no differences because this is just, these are all numbers, right? And these are all numbers, right? And the idea is that if you add these up and multiply them each by a coefficient, that's going to be equal to y, right? And so we have the sum of f of x's and y. So what that can look like is if we just have one x, or let's say we have let's say we have these x values, right? And we have a function here. The function is going to be b0 plus b1 x plus b2 x squared plus b3 x cubed, right? That's supposed to be a 3 there, right? So this is a polynomial, right? And this function, it has a constant, right? B0 is a constant. B1 is multiplied by x. B2 is x squared, right? And B3 is x cubed, which looks like that, right? And these, so what we're going to say is that to make this homologous with the previous one is that f0 of x is equal to the number 1. f1 of x is equal to x. f2 of x is equal to x squared. And f3 of x is equal to x cubed, right? So now we have a polynomial, right? And we've got data points. And we want to ask ourselves, is there a set of coefficients, B0, B1, B2, and B3, that if we multiply them by these and add them all up to get y, right? Get x sub I there, x sub I, x sub I, x sub I, and then we got y sub I, right? That in this, is there a set of coefficients or b values that minimize or that make the data fit the model, right? So we want to find those coefficients such that the model fits the data, like that. And so in general, this is very possible. And this is done using a tool called LinEst. And LinEst is just least squares regression. And LinEst, it's going to give you B3, B2, B1, B0, and then uncertainty estimates. In all of those guys. And it'll also give you more statistics. It'll give you 3 more statistics, and then it'll give you nothing out there. So it makes a little matrix, right? And but what you're really after when you do LinEst is you're after these values primarily and these values sort of secondarily, the coefficients and the uncertainties. So let's see how we can envision a LinEst type of function working. Okay, so let's go to a simple model, the model of a line where we have y equals b0 plus b1 times x, right? And this is the intercept, and this is the slope, right? And f0 of x is equal to the number 1, and f1 of x is equal to x, right? These are really simple functions. There's no sines or cosines or exponentials or anything. these are just simple values, right? So as you know, the data to fit a line might look like that, right? Here we have y and x, and this is y sub 1, x sub 1. There's y sub 2, x sub 2, y sub 3, x sub 3, y sub 4, and x sub 4, right? But the data points are right there. And we want to say, well, is there a line that best represents these data, right? Is there a line that can make like, for example, if y is a signal and x is a concentration, and we want to use this curve to relate the instrument signal to a chemical concentration, for example. And how can we do that? So so for example, like this could be absorbance and this could be concentration, right? And if we get an absorbance of 0.251, right, we want to know to what concentration, this corresponds, and this might be, 0.00423 molar, something like that, right? So we need these coefficients B0 and B1 to define the line here, right? And this is going to be y equals B0 plus B1x, right? That's the line. And then if we have an x value that's, we can actually solve this for x, right? This is a weird backward thing that analytical chemists have gotten into. And what we would do is we'll solve it as signal as a function of concentration, and then we will get B0 and B1. Then we'll say that y minus B0 over B1 equals x, right? And then we'll plug in 0.251 minus B0 over B1, and that will give us our x value, which is 0.00423, right, in this case. So, so this is what we're up to. And this in general is called modeling, right? So let me focus down just a little bit further here. Now let's take a set of data points again. And then we're going to stipulate a best fit line there. And we're going to say how can we quantify the fit between these data points and this line, this prediction line, right? Well, let's define for each point the vertical chord that connects the data point and the line, right? This is x sub I, or x sub 1, y sub 1. And this point here is x sub 1, and then yp sub 1, the predicted y value, right? And then up here, we have x sub 2, y sub 2. And this guy here is x sub 2 and then yp sub 2. And similarly, we have a set of other data points there. And now we can start thinking about saying, well, you know, this x1 y1p, right? What's the thing that defines the goodness of this fit is y1 minus y1p, right? It's that distance, and then there's this distance to compare, right? And there's y2 minus y2p, the predicted value. That's this distance here. And then y3 minus y3p and y4 minus y4p, right? And we can say, well, what can we just add up these error values here, right? And get a total error. Add up all these values, and we can call this R1, this is R2, R3, R4. This is called a residual, right? And can we add up all those residual values and have those residual values the sum of R sub I, estimate the goodness of the fit? And you can almost do that, but there's a problem, because if you have positive and negative R values, then they tend to cancel out, right? And in that way, it's like even if this were here and this were here, the residuals to that would be, this would cancel with this, right? Because this is large and positive, this is large and negative. So what we can do is we can square these values. And this is R1 squared, R2 squared, R3 squared, R4 squared, and this is sum of R sub I squared, right? So now what I'd like to do is I'd like to give you guys a little quiz right now. And I would like for you to predict for me what the functional form of, I'm going to call this, give this guy a name, call this chi squared, is equal to the sum of R sub I squared. And let's just say that this m right now is m is equal to 1, right? So I'm going to put, I'm going to make this axis m, right? The slope. And this is the value 1. And I'll just say, for example, right now that, let's say that 1 is the optimum value for the slope, right? So any perturbation you make to the slope is going to make the fit worse, right? So you can go, if you go up, then the sum of these values is going to be the chi squared for this. This is a large m value. And that will give you a larger error. And that will give you a larger chi squared, right? And so what I'd like for you to do is to predict for me what the functional form of chi squared as a function of m is. And I'm going to put a single data point on this curve. and I'm going to give you some choices to make, right? And I'm going to say that it might look like this. It might look like this. It might look like this, and it might look like this, right? So we'll call this A and B are the straight lines. C is the parabola going up, and D is the parabola going down. So A is straight with a negative slope. B is straight with a positive slope. C is convex up. And D is, C is, let's say it's parabolic up. And D is parabolic down, okay? So somebody start me off with a question about this, about the question that I just asked you. Like, you could propose an answer or something like that, or you could try to ask a good question.
Could it possibly be that it's B as the answer?
Okay, so positive up, good, all right. Now, so why do you think it might be B?
I feel like if you were only looking at chi, and the relationship between chi and M, then it would be one of the parabolas, because that's when it would be, they would be quadratically related. But since we're looking at chi squared, I feel like that's something that that increases linearly as M increases.
Okay, all righty. You're on the right track. You're totally on the right track. So let me get the chat window back here. So let's see. Oops. I just have to get this. So.
Wait, but chi can be negative. That's right.
So, okay, so Anne wants to say C because it's squared. So in my head, it'll never be negative, but you can have the same Y values for both positive and negative values. So she's a little bit lost. Okay, that's good though, that's good. That's excellent progress. So let me ask somebody else to weigh in. Let's get just a few more people to weigh in with a thought or a question or something like that, right? So maybe.
Oh, sorry. I was just gonna say, I think I agree with Anne, because I remember back in math, there used to be like rules where there's certain shapes. So like x cubed was like a squiggly across the graph or whatever. So I think it's a C because it's x squared is a parabola. I don't know if I'm remembering it correctly though.
Okay, all righty. So, really, we don't even have to think about all of them. We could just think about one point, right? And if we don't change the intercept here, then what's going to happen is we'll have a family of curves that go out like that, right? And if we just take this data point here, right, then You can't see anything here. Here, let me get a new piece of paper here, and I'm going to say, I'll draw a reasonable guess, then a sort of a couple of unreasonable guesses, and a couple of more unreasonable guesses, right? And let's just talk about, say, this point here. There's chi1, right? And then there's chi2 and chi3 and chi4 and chi5, right? So, or we could say this is, or if we want to put them in order, let's say this is 1, 2, 3, 4, and 5. So there's a slope 1, 2, 3, 4, and 5, right? So slope 1 has this, so we can say M1 gives us R1, which is -6, right? And then M2 gives us R2, which is maybe -2. M3 gives us R3, which is maybe +2. And M4 gives us R4, which is, maybe +10 or something. It's this longer chord up there, right? So now what we're going to be doing is squaring and adding the R values, right? So we've got R1 squared plus R2 squared plus R3 squared plus R4 squared, right? And R1 squared is 36, R2 squared is 4, R3 squared is 4, and R4 squared is 100. So if we add all this, we've got 144 as the chi-squared, right? And we see that if we go between in order from the M1 to M2, M3, M4, like that's M1, 2, 3, 4, 5. Actually, I've got 5 of them there, sorry. But we go from a positive value to a smaller value to a smaller value to a positive value, right? Does that make sense? So what then would that look like if we were to plot R squared versus M? We've got, let's say M1 or M is, let's say -5, -1, 2, and then say 4, right? And then R squared is going to be 36, 4, 4, and 100. And so we've got -5, -1, 2, and 4. And this goes 36, 2, 2, and 100. Well, maybe 100 would be up here, right? This is 2, 2, this is 36, and this is, say, 100. I know my drawing is complete crap and not to scale, but the idea is that this is going to go down and then up again, right? Does that make sense? So we're just sort of saying, how is the error function going to vary with our guess of the slope M? Anne, what do you think? Snigdha?
I guess that makes more sense now looking at it, especially because if we said it was linearly related, then chi could have been negative. Chi squared could have been negative, but chi squared can't be negative. That's not logical.
Right. Chi squared can't be negative because it's the sum of a bunch of squares, right?
Yeah, that makes sense.
Okay, cool. Jeffrey, are you with us today?
Yes, I am.
Okay. Any thoughts on this or?
No thoughts. I'm just kind of
Okay.
grasp it. Just kind of
Okay.
really visually see it. Yeah.
Okay,
but
cool.
I understand it.
Okay, cool. Logan, are you hanging in there?
Yeah, I'm hanging in here.
Okay, all right, cool. All right, so I'm going to change my screen here to, here, let me do this. Now let's see, am I sharing now a Word document with y'all? Or no? Probably not here. Let me see here. I'm going to go to new, okay, I'm going to go to new share, screen one, there we go. All right, so now I'm sharing a Word document. I'm going to make it bigger. Okay, so here's what I've just done is I've just defined chi squared here, right? Chi squared is the sum of y sub I minus b0 f0. I just am omitting the x, f of x, right? And b1 f of x sub I, b2 f of x sub I, right? Right? And so do you agree that chi squared as a function of b0 should be a parabola that goes up and then down and then up again as b0 changes? Now, if you hold b1 and b2 constant, it's reasonable anyway, right? It could be. That's a reasonable idea, right? You got y minus b0 f0 squared, you got some plus some other things, but these are constant, right? You got y minus b0 and this whole thing, y minus b0 f0, that's squared, right? Then we're going to look at chi versus b0, right? B0 is the parameter that we're going to optimize, right? So now what we're going to try to do, and this is a huge sleight of hand. So make a mental note that you're going to get lost right here, okay? And then you can challenge me later. But the partial derivative of chi squared with respect to b0, right? This is the slope of a parabola, right? And the slope of a parabola is negative, 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 0, positive, positive, positive. Right? Let's look at that again on the paper. Right? We've got the slope here is negative, negative, negative. Then right at the bottom, the slope is 0, and the slope is positive, and now it's positive again, right? So the partial r squared by partial m, right? That is gonna be a new function which is kind of like that, right? This is going to be, and this is versus m, and then it's going to be 0. So the value is going to be 0 down here, right? When that's the m value here, that's the m when this is optimum. Right. So what really I'm trying to say is that this finds the minimum. Is that when you set this to 0, then you're set up to find the m, oops, that makes r squared a minimum. Does that make sense? Somebody say, yeah, that makes sense.
Yeah.
Yeah, I love it. Cassie, does that make sense?
Sure.
Okay, all right. So when you take the partial derivative of when you take the derivative of a parabola and set that equal to 0, then you're saying that the value, the x value, right, is equal to the x value at the bottom of that parabola. Does that make sense? So if we have, like, for example, let's just say we have the parabola y equals x squared, a real simple parabola. Whoop. Yeah, and we're going to say dy by dx equals 0, right? And dy by dx is equal to 2x is equal to 0. And so in this case, x is going to be equal to 0 divided by 2. So x is going to equal 0, right? And that is the point at the bottom of that guy right there. So this is what we're doing if we have a parameter here, This is like r, okay, so anyway, I'm getting confused here, but we're finding the minimum in a parabola. Okay, so let me go back to the Word document here, right? So here we've got chi-squared versus b0. We're setting that, we take the derivative of both sides, right? Partial of chi-squared with respect to b0 is equal to the partial of chi-squared with respect to b0 of all this stuff, right? And really our ability to do this is just dependent on our ability to solve this equation here, right? And all we have to do is apply the chain rule to sort of sort it all out, right? So the derivative of f of g is f prime of g, g prime of x. And that that's a chain rule that works, right? So now what we're going to do is we're going to say f is the square and g is y minus b0 plus b1 plus, it's the inside of the square, right? What's inside the square there, right? So we're going to say 2 times, so f prime is 2, x, right? There's x, f prime of g, and then g prime of x is the partial with respect to b0 of this stuff, right? And so we're going to say 2, we're going to pull out the 2, and we're going to say This is 2x, right? And the partial with respect to B0 of this is just F0, right? Now, the fact that now we can add them all up, right? But the math doesn't really change when you add them up, you know, so we're gonna add up all these terms. And so then we have, now what we're gonna do is we're gonna try to arrange this in a way that it can be solved, right? For all of these guys simultaneously. So just, you know, sit back for a minute, don't worry about the details too much, and I'll walk you through the rest of this, right? This is the optimal value for B0, right? Is when d chi squared dB0 is equal to 0. And so let's pull B0 out of this, right? Well, let's start by we're going to separate this 2y f minus 2 f, right? There's 2yf equals 2 this sum times f, right? You're just going to pull them onto opposite sides of the equation there, right? And now we have the f values and the y values all on one side, and the b values and the f values on the other side. So here is one of what are called the normal equations. And we actually have a different normal equation for every b value, right? Because we have to simultaneously optimize in B0, B1, B2, etc. Right? So here is, and when we optimize for B0, we get F0. So we're going to take B0, F0, and then it's this F0, right? Then this F0, and then this F0, right? So this is the partial with respect to B0. This is the partial with respect to B1, because it's always multiplied by F1. And this is the partial with respect to B2. It's always multiplied by F2, right? So now, if you think about this, you have y values, which are just all a bunch of numbers, f values, which are all just a bunch of numbers, b is an unknown times a number, plus b1 times a number, plus b2 times a number, right? So really, you just have number equals b0 times number plus b1 times number plus b2 times number, right? Then you've got another way to do it. New number equals b0 times new number plus b1 times new number plus b2 times new number, right? And when you work down through this, you see that this is ripe for the pluck it, because this is a linear algebra problem where you have number is equal to number times this array of three numbers here, this B matrix. And all we need to do is take this thing here and invert it. And matrix inversion can definitely be done, right? So you find the inverse of x, multiply it by this. This is called the y matrix. That'll be inverse of x times b, which is just b. And so then once you've found the inverse of X, you multiply by Y, and you get your little matrix of B values out. And that's really all I want to say about that, right? Now we can do that with some data here. And I'll go ahead and I'm going to pull up Excel, and I'll just give you an example of how that works. Let's see here. Share. Blah, blah, blah. Okay, where are you? I have to actually cancel that. Let's see. Go to blank workbook. Stay, share, one Excel, okay? All right. Share, one Excel, there we go. So here's a blank Excel data point, right? Data workbook, right? So let's make an X matrix here. Make it 0, 1, 2, 3, 4, 5, 6, 7, right? And now I'm going to make up a function here, and then I'm going to get the coefficients back. And the coefficients are going to be B0 and B1. Actually, I'm going to call it B.1 and B.0 because otherwise they look like cell addresses. So B.0, let's say this is 3.14159. And B1, let's say this is 1.12.345, right?
Professor?
Yes?
We can't actually see what you're doing.
Oh, you can't? Is it too small or is it like invisible?
It's
too small.
invisible.
Oh, okay, sorry. Let's see here. Can you see it now? Oh no, it says pause. Oh, there we go. Can you see the worksheet now?
Yes.
Okay. All right. You sound so disappointed though. Okay, I promise it'll get better. Okay. So we've got I'm going to make this much bigger here too so you can see it. That better? We've got X values, X sub I, Xi, and now we're going to make Yi, right? The Yi is going to be, I'm going to just turn these guys into formulas here. So formulas, grade from selection, top row, whatever. So, and now let's n.1, let's do an n, let's make that n equal to 5. I gotta get this guy into the formulas too. Okay, so let's say that we're gonna make this equal to b.0 plus b.1 times x, right? But I want to add some noise here. So we're going to say plus rand times n.1. Okay. So now every time I do anything, that number is going to change a little bit. So get used to that because it's going to recompute the random number every time, right? So now we have a set of data points here. Now we want to find the B0 and the B1 value that best fit these data, right? So let me insert a chart, which is, let's just do scatter and select the data, add X, Y is going to be there. Oops, it's got that stupid 1 plus there. Okay. All right. So there's our data, right? I'll make this guy a little bit smaller. And what I want to do now is I want to find a chart value that makes this all work, right? So, or I want to find the B values that make it work. So I'm going to do, I'll just highlight a 2 by 2, right? And I'm going to say equals linest of the known Y values, comma, the known X values, comma, true, comma, true. And now I'm going to say Shift Control Enter there. Okay. So now so I'm actually going to move this a little bit. This is B0 estimated, right? And this is B.1 estimated, right? Notice that the B1 seems a little closer in magnitude, right? 11.9 is fairly close to this guy here, right? So I'll put that guy there. I'll put that guy there. So you can just see how they are, right? Now let's type this. This is going to be B0 estimated plus B1 estimated times this guy here, right? And you'll see that this lines up okay. Oops, sorry, I screwed up. I gotta put an F4 there. And then F4 there. Oops. Ah. No, I screwed this. Yes. Gotta rewrite the whole thing. So this guy here has got to be equal to G7. Here that's F4 plus F7, F4. There we go. Now I can drag this guy up a little bit, and I can drag it down. And you'll see that these guys, oops, don't look anything like that. Let's see here. This is B0 plus B1 there. Yeah, that's right. Oh. Oh, I'm sorry. I got these wrong there. It's supposed to be up there. There we go. Now let's see here. There we go. So now these are the estimate. These are Y predicted, right? Now let me add this data here. I'm going to add this second column. X values will be here, and the Y values will be here. And let's make this second series here. This is going to be a straight line, right? So this guy is going to be net selection. Solid line marker, options, none. Okay, there we go. So let me make the make this 25. So now we can see there's like more noise here. But by doing linest here, we can say this is equal formula text of, just say this guy, right? That'll show us what the formula is there. And so we can see how, even though the data are snaking around there, the intercept and the slope functions optimize to the data each time it's updated, right? And there's really no limit to the number of like you can put in a bunch of X variables and get a bunch of coefficients out of that guy. So what is the take-home message from this? Well, the take-home message is that if you have to model data, you can do so using this function called linast. B0 and B1 come out here, and then their uncertainties come out here, right? And when you get to the part where you're doing the homework, or actually when you're doing the lab report, you're going to use linest and the uncertainties and other parts of it, and then you'll find then you'll be able to derive the information that you need from the table. So let me actually grab those guys here. So I'm going to go back to Canvas. And I'm going to get, oops. Let me go to Files. Let's see if they're here. Lab, HPLC. Aha. So I need to actually get these into Canvas. But I'm gonna dig them off of my hard disk here real quick, and then I will show them to you. Okay, where are you going here? I see. Okay. Okay, so now I'm going to do a new share, and I'm going to say this guy. Okay, can you see this pretty detailed spreadsheet right here? Guys?
Yes.
Okay,
Yes, we can.
great, thank you. So, so what this is, first we do the crystal violet experiment, and there's a spreadsheet like this for crystal violet, and I'm just sort of forecasting ahead a little bit, and I'm showing you the spreadsheet for HPLC, which is our second experiment. It's experiment 1, right? And there's a bunch of, you have to do a bunch of weighing here, right? You're getting tare values, et cetera. This for the benzoic acid, the caffeine, and the water, et cetera. And this is going to calculate the concentration of a bunch of standards. And then when you run each of these standards on the HPLC machine, you'll get these. The standards will have these 3 concentrations, and you will get these. For example, you'll get 3 signal values like these 3 signals. And then you're going to run an unknown sample here. You'll get its signal, and then you use that to back calculate its concentration here, right? So that's the sort of the meaning of this. There's X and Y. There's 3 by 3, right? And then there's a fourth value here, and then there's the x value that you derive from that there, right? And what I want to show you here is that this guy here is a big linest, right? So this is, oops. So I can say that here this is equal to the formula text of this guy here. Oops, sorry. I think I just want to make it T6. All right, so this is the formula. This linest here is actually referring to these concentration and signal data here, right? And these guys are giving the intercept B and the slope M of these data points, right? Then you're going to use this slope and intercept and then this value to get this guy, right? It's y minus b divided by m. Y minus b divided by m. You know, y equals mx plus b, and x equals y minus b divided by m, right? And so this guy here is y minus b over m, right? So that's just one way that we're going to be using linest going forward. And then there's a whole bunch of mathematics then that goes into calculating the uncertainties. And the uncertainties use another value here called S sub y. And then it uses a derivative of the x values here as well. So I'm going to spare you all that right now, but this is where we're going with all this stuff. So I didn't leave any time, but I want to ask, are there any questions on the homework for tonight? There's a homework due at midnight tonight. That's homework 4. You guys are very quiet.
Professor?
Yes?
Can I ask a quick question about number 11, please?
Sure, absolutely. I'm going to change the share to my browser, and then I will, there we go. And I'm going to pull this down here, and it's probably going to pause. There we go. So let me get here. Home. Check the VOA. Load it in a new window. You guys can see all this happening, right? Hopefully. Mm-hmm. Okay, number 4 or number 11?
Number 11.
Okay, cool. Comparing methods, great. Okay, right. So I have to make this bigger, right? Okay. So good. Okay. Yeah, this is a little bit tricky, right? You've got, these are type 2 t-tests with n equals 5,
Mm-hmm.
right? So do you know what the there's a formula, right, in the notes to do this. And I'm gonna, yeah, but go ahead and ask additional questions about this if you want to.
I was able to do it because I was able to see that the standard deviations were both very similar to each other. So I was able to use the formula. But the question that I had was, earlier in the homework, they had shown us, one of the questions showed us an equation for a method of solving T, which had to do with comparing differences of individual measurements of individual samples that were obtained using different methods. And I was wondering why we couldn't use that here.
Right, because these are, that particular approach is when you measure different things, like method 1 and method 2 on one thing, and then you move on to another thing. You do method 1, method 2, then you move on to another thing, you do method 1, method 2, you move on to another thing and you method, and you don't have any replicates of the same thing, right? So it's kind of a weird example, like, why would you do it that way? If you want to compare the standard deviations of a couple methods, but that I don't think we're going to be using that test in basically anywhere in the class. I don't think it's going to come back, and I'm not going to put it back, right?
Okay.
Yeah. So what you do here, I'm sure it's probably right down here, right? Is you calculate the F value for the standard deviations, and these are all going to be the same, right? 0.68 to 0.7, and then 1 and 1, or 0.68 to 1 and 0.7 to 1. So these are the two different ways you can slice this. The standard deviations are all the same, right? There's no way that you're going to get an F value that's larger than 1 over 0.7 or something like that. It's going to be 1.2. So once you get that, right, your F value is 2.16. Your F critical is going to be like much greater than that, right? So you use S pooled like this, right?
Yes.
And then you get the then you can calculate the T value, or I'm sorry, that's S pooled again. Then you can calculate the T value like that, and you get the T value is 1.39 in this case. This is for sorry, I gotta make this guy a little bit larger. Can I make it larger? Not sure. There we go. I can. This is for. You're going to compare FAAS to this new method, FAAS and the other method, right? And the EDTA method, right? And then you get it. You get a T value, and that T value should be much smaller than the T table. Right? Because the methods are giving very similar answers within error.
Right.
Yeah. Or I'm not exactly sure what answer you got, but sorry, sounds like you're very close there.
Yeah, that makes sense.
Okay.
I had a question.
Yes, absolutely, Jeffrey. Yes.
It's on the chapter 5 homework, number 4.
Chapter 5. Okay. I haven't even looked at that yet. Do you want to hold that till next time so we can get other folks sort of on the same page?
Yeah, that's fine then.
Okay. Thank you. Thank you, guys. Okay. we will see everybody. I'll see some of you in the morning at 9, and then I'll see everyone will see me anyways next week next Monday at 6 p.m. Okie dokie. Thank you.